So, ladies and gentlemen, if you could please take your seats and get ready for this afternoon's lecture. My name is Chris Atkin. It is my great pleasure to welcome you to the ICAS 2022 Enoch Tulin Lecture for Innovation in Aeronautics. This lecture and the award that goes with it has a purpose to recognize contributions of an individual or a team in effectively integrating a suite of advanced technologies combined with new design and or manufacturing processes to create a new aeronautical system with significant worldwide impact. I will give you the details of the citation shortly, but the tradition is to name the lecture each Congress after a local innovator from the country of origin, country hosting the Congress. So I'd like to invite Anders Gustafsson of ICAS and the local organizing committee to come and tell us a little bit about Enoch Tulin. Anders.
Yeah. Could we have this first slide of Enoch Tulin, please? Yeah. You may wonder, but he just explained that when this award was established in 2006, it was decided to name it like this, and today we celebrate Dr. Enoch Tulin. And who was he? He was a Swedish aviation pioneer and industry leader. He was born in 1881. There it is, yeah. He was born in 1881. He studied aeronautics in France and received a doctor's degree in Sweden and a French pilot certificate in 1913. In the early years of flying, he created interest and financial basis for aviation in Sweden. And he founded his aircraft factory in southern Sweden and started to building French aircraft, more than Saulnier type. And then he had an aerodynamics laboratory, and he also ran a flight school close to his place in southern Sweden, where about 100 pilots were trained at his early days. And after some time, his company had about 800 employees. But then he died during an air show in 1919, and the war was over, and there was no demand for his aircraft, so his company went bankrupt very soon. But to his memory, we have the Tulin Medal by the Swedish Society of Aeronautics and Astronautics, and this memory medal was instituted in 1944, and it's the most prestigious award for aviation and space in Sweden. And it's available in 3 denominations: gold, silver, and bronze. So then you have the background about Enoch Tulin and why this lecture was mentioned in his name. Thank you.
Thank you, Anders. So the ICAS Award for Innovation in Aeronautics 2022 is awarded to Professor Eli Livne from the United States of America for seminal contributions to the theory and practice of aero-servo-elasticity in the context of aircraft multidisciplinary design optimization, and for pioneering work towards the maturation of aircraft active flutter suppression technology. So let me tell you a little bit about Professor Livne. He is the Boeing Endowed Professor of Aeronautics and Astronautics at the William E. Boeing Department of Aeronautics and Astronautics at the University of Washington in the United States. Professor Livne holds a BSc 1974 and an MSc 1982 degrees in aeronautical engineering from the Technion Israel Institute of Technology, and a PhD from 1990 in aerospace engineering from the University of California, Los Angeles. After obtaining his undergraduate degrees, he served in the Israeli Air Force in research and development roles. And after graduating from UCLA, Professor Livne joined the faculty of the William E. Boeing Department of Aeronautics and Astronautics in 1990. So over the course of his academic career, Professor Livne has continued extensive collaboration with industry and government organizations. Highlights include structural and aeroelastic optimization and lightweight airframe design with Boeing commercial aircraft, membership of the NASA Boeing High-Speed Civil Transport Aeroelastic Concept Evaluation Team, and the associated Aeroelastic Working Group, and active Flutter suppression work for the FAA, and contributions to aeroelastic wind tunnel tests of highly nonlinear flight vehicle configurations, as well as active aeroservoelastic control. Professor Livne headed the airplane design, education and research program at the University of Washington for many years. His accomplishments were recognized by a number of awards, including the 2021 AIAA's Holt-Ashley Award for Aeroelasticity. With his extensive expertise, Professor Livne's research has been funded by NASA, the FAA, the Air Force Office of Scientific Research, the ONR, NSF, and by Boeing. He was an associate editor of the AIAA Journal and a guest editor for the Journal of Aircraft Special section on MDO, and one of the launch section editors for the Encyclopedia of Aerospace Engineering. Currently, Professor Livne is the editor-in-chief of the AIAA's Journal of Aircraft and is a fellow of the AIAA. Eli, please come and deliver your lecture.
Thank you. Hi, everybody. I can see you very well because the lights are in my eyes. Let me check that this is okay. Thank you very much to ICAS for this award, which is really humbling. You know, unlike poetry or philosophy or painting or sculptures, aeronautical engineering is a team effort. No single person ever does anything by him or herself. So this award made me reflect a little bit on my life in aeronautics and realize how fortunate I am to have worked with such great people, great colleagues who became friends over the years. Everything that I've done was done because of them, with their support. And I'm very, very grateful for them. I want to mention my great professors, Eli Nissim at the Technion, a pioneer of active flutter suppression, Lucian Schmidt at UCLA, the father of structural and multidisciplinary optimization, Peretz Friedman, one of the finest aeroelasticians of all time. And here in the audience, my colleague and friend, Dr. Kumar Bhatia, who found me at the University of Washington 3 months after I arrived and hired me to work with him at Boeing on this grand vision of how airplane design could be revolutionized through optimization. And he carried this stubbornly and diligently against many odds for more than 30 years at Boeing to bring Boeing to the level of excellence in this area that they are today. So many, many thanks for these great people. Of course, there are more people that I owe a lot to, and I mentioned some of them during my presentation. Okay, so what is the goal of this talk? I want to try to convince you that it is important to bring active control to the early stages of airplane design, that while it is difficult, it is feasible, it is doable. I want to briefly talk about the state of the art, since this can be viewed as a bit of an esoteric area. I'm going to insert 1 or 2 short tutorials into the presentation to make sure that we're all on the same page. And I want to formulate the multidisciplinary design optimization problem with aeroelastic control in a general way that hopefully will serve other people who develop this technology. And then I'm not going to hide from you that there are some debates and some disagreements about the way we should proceed. So a very short tutorial about engineering optimization. We think about any system as a set of systems or a systems that can be parameterized and can be described by mathematical models. These mathematical models have parameters which determine what these systems are about. And as designers, we play with these parameters in order to get the systems that we want. So in the case of a structure, for instance, even if the material is already selected and the shape is given, we can still ask ourselves what is going to be the best structure, maybe the minimum wage structure or the minimum cost structure that will meet all design requirements with the safety that we need. That's really the essence of the problem. Following Lucien Schmidt's terminology, I kind of have a little picture here of one of his papers about the development of the history of structural optimization. Those parameters that define these systems that we are designing can be split into two. The pre-assigned parameters, these variables that we are not going to touch during the optimization, and those design variables that we're going to play with during the optimization. All of the constraints, all the requirements are described by mathematical functions of these parameters. The stresses in the elements, the buckling loads, the flutter parameters, the aerodynamic parameters, everything that the system does can be described as some function of these design variables, and we're going to put them in a list of what we call constraint functions that will limit us, will tell us what we can and what we cannot do in order to get feasible designs. And then there is the objective function. What are we trying to minimize or maximize? Is it the cost? Is it the performance? And so on the right is the mathematical formulation of the problem, minimize some function, some objective function of the design variables and the pre-assigned parameters over the set of possible feasible design variables and meeting all these constraint functions that I mentioned. Structural optimization is about optimizing structures. So you ask yourself, what is the best structure that I can build that will minimize the weight, minimize the cost, maybe maximize reliability, subject to all the stress constraints, maybe natural frequency constraints, maybe fatigue constraints, all those limits that will ensure that the structure is safe. And extending it to aeroelasticity, in a minute I'm going to say something about aeroelasticity, the field where structures and aerodynamic forces interact, when the structures are flexible and they determine the forces acting on them. Now we have a problem where if we focus on the structure, we want to design a structure of minimum weight or minimum cost that will meet constraints on all the stresses and the buckling loads, but also on some aeroelastic measures, such as flutter behavior, efficiency of ailerons, and things like that. So again, aeroelastic phenomena are due to the interaction of flexible structures and the unsteady aerodynamic forces that act on them. In this list, you can see a number of them, what we call handling qualities. These are the constraints that will tell us how airplanes behave. And remember, we're talking about flexible airplanes. So they don't only move as rigid body in space, they also flex. How would the pilots feel about them? How would the control system manage to work with them? So this is all the field of handling qualities. All this can be described mathematically. Maneuver loads. These airplanes maneuver. And so you want to make sure that in all possible maneuvers, nothing fails. All the parts are within the stress limits, within the buckling limits, within the frequency limits. Flutter is an aeroelastic stability, where as the speed or dynamic pressure go up, a kind of a feedback loop can lead to an unstable behavior. I'll show you an example of this in a few minutes, so I don't want to talk too much about it now. And then the issues that you all know. You fly on passenger airplanes, you know the important issue of ride comfort. Airplane begins to hit turbulence, shakes a lot. And so how do you design airplanes where that level of shaking will be tolerable? Passengers will tolerate it, and flight crews will tolerate it, and structural fatigue. So these are typical constraints. These are typical design requirements in the aeroelasticity fields that add to the structural requirements. So how do you deal with it? How do you design airplanes that would meet these constraints? The traditional way was what we call the passive way. you just basically design the structures that would do it. If the structure is too flexible, you beef it up. You make it stronger, you make it more stiff, you add weight. If you can use composites, then maybe you don't add weight, but you can play with the fiber direction, so you can tailor the stiffness, and you can control the stiffness distribution. You can decide to move masses, place the engines here, place the engines there. If you have no choice, you will add ballast masses. And so in order to solve dynamic problems, and all this has been used for years, was used for years. The problem with this is that in almost all cases, this will add significant weight to the airplane. And not to mention cases where you think you've done everything right, and now you have the prototype, and you already invested $7 billion in developing it, and something was missed, and you have an aeroelastic problem, and what are you going to do? Redesign the wings, redesign the structure. So usually the penalties here will be very, very heavy when you use the passive approach. So I would say in the 70s, definitely the early 80s, it was clear that structural optimization should be expanded to cover aeroelastic optimization. And some great airplanes of the past were designed using structural optimization with aeroelastic constraints, the X-29 forward swept wing with composites, the F-16, the Rockwell X-31. It was clear that this was the way to go. Industry, unfortunately, does not share with us enough of what they are doing. So it's not so easy to know what the capabilities are at different companies. Lucky for us, actually, Dassault in France managed to share with us quite a bit. They were pioneers in developing aeroelastic optimization techniques going back to the 70s. Christian Petier, their real genius of an aeroelastic designer, developed and led the development of a code named Livne. And here is an image that I stole, basically, from a recent paper by the head of structures at Dassault, which shows the development of Livne. So moving from the left to the right, you can see what they can do in the 70s and the mid-70s, basic airplanes, to what they can do now with very detailed mathematical models of airplanes covering a host of constraints, amazing capabilities, which I know, even though industry does not tell us, that now Boeing can do and Airbus can do. So these capabilities are existent. Now, optimization has not been only attractive for structural and aeroelastic designers. Control system theorists and control system practitioners knew that it was important for them to design best control systems. So you just go to Amazon and you search for books on optimal control, and here you are. So the fact that you can design control system not just to do the job, but to do the job in some best way, covering constraints and other design requirements was very well known, and the technology is quite mature. So it was natural to ask if we could add active control to aeroelastic systems in order to improve them. So in this figure, on the bottom two blocks in blue, you can see how the flexible structure interacts with the aerodynamics in a kind of a feedback loop. You apply forces to the structure deforms, the deformation changes the aerodynamic loads, this feeds back, and that can lead to all these aeroelastic problems. And on top in red, you say, well, you know, the structure is moving, it's moving in space, it's deforming, let's place some sensors, accelerometers, strain gauges, and let's use the signals from these sensors that tell us about what they are doing in order to feed a controls computer that then would set commands to the actuators that would move control surfaces, and this way affect the total behavior. So in the area of active control of aeroelastic systems, first you think on maneuver load control. Here the idea is that you will design, structurally, you will design your airplane to, let's say, cruise conditions. And you can see here in the broken line the perfect distribution of loads on the wing. Of course, you worry about the bending moments along the wing because that will determine the weight of the structures that you will need. But if the airplane maneuvers, pulls some G's, turns, these bending moments will go up unless you use the control surfaces in order to redistribute the load. So you can see here in the solid line how, as the airplane maneuvers, the control surfaces go up or go down, and the whole distribution will change in order to keep the loads within limits so that you don't have to add the weight. As I said, we all flew through gusts. This is a daily experience for anybody who flies flexible airplanes, hit bumpy air, and they jump, and if you look out of the windows, you see the engines moving and the wings flexing, and everybody gets very scared, except that when you know how safe they are, you shouldn't be scared. I get scared, even though I know that this is safe. Helps my kids, by the way, when I tell them and even know how to design them, I still get scared sometimes when the airplane shakes too much in flight. And so here again, if you have an active control system, as the airplanes begin to shake, the control surfaces can move dynamically based on some control law in order to reduce this level of shaking and control the dynamic stresses and the levels of vibration. And here is ride comfort. Well, we think about passengers in airplanes, but this is also a military problem. This famous story of the B-1 bomber. It was designed, it's a supersonic bomber. It was designed for a mission, typical mission of going very high into enemy territory and delivering its ordnance. But with the development of advanced radar systems, the mission changed. And the airplane now was required to fly at treetops, basically, using terrain following. So imagine a heavy bomber like this, very flexible, very slender, flying in canyons and over hilltops, really shaken by very turbulent air. The crews couldn't sustain it. The crews couldn't stand the levels of vibration. So North American Rockwell at the time, now it's all Boeing, installed these little two control surfaces in the front, the little vanes, and with the active control system suppressed the vibrations. I talked about the flutter problem. As I said, this is an instability. Airplane begins to fly faster and faster. That feedback that you saw, as the airplane deforms in a dynamic way, it would change the aerodynamic forces. The aerodynamic forces would then feed back and change the load of the airplane. If you're not careful, if not designed properly, you will get an unstable oscillations that can destroy an airplane in a fraction of a second. This is a famous story from the 80s. NASA developed a special drone for aeroelastic research. It was called DAST, D-A-S-T, for drones for aeroelastic and structural testing. And they had an active control system, and all the great people of the time designed control laws. And lo and behold, in one of the tests, there was a miscommunication between people, and they programmed the wrong control law to this drone. They realized that this was the case, and they started to slow it down, but it was too late. On inertia, the airplane was was accelerating. If you look at the figure in the center, and I by the way, apologize, I imagined a screen where I'd be able to use a laser pointer to point. I did not imagine such a huge screen, so I will direct you just by telling you what to focus on the slide. So when you look at the center, look at the bottom, you will see the Mach number going up with time. As the Mach number going up, the airplane becomes unstable. The control system tries to do something, but it's too late, and the airplane breaks into pieces in a fraction of a second. So it is a very dangerous phenomenon, and you cannot allow any airplane to ever encounter this kind of a phenomenon. And the passive solution here will be stiffness and the correct mass distribution, but maybe we can use active control. And maybe we can control or program the control surfaces to respond to motions in a stabilizing way so that we don't have to add all the weight to the system. So here is the story. First, you can see the flexible airplane, the deformable airplane in flight. It is driven by inputs. These inputs come from pilot commands to the actuators and from gusts in the atmosphere. It responds by moving, and it's moving around as what we call a rigid body, and it's also flexing in flight. You have a set of sensors that measure this deformation. They feed this information to a bunch of control laws that are on a controls computer, and these control computers send inputs to the actuators to close the loop and to create a system that using active control will meet all these requirements on flutter stability, dynamic loads, ride comfort, fatigue, and so on, without having to add substantial weight to the structure. This was already envisioned in the early 50s, but the technology was not there in order to do it. Late in the 60s, the US Air Force gave Boeing Wichita, when Boeing was still in Wichita, a contract to test it on a B-52 bomber. So Boeing took a B-52 and modified it by adding control surfaces. I'm not going to go into the detail, but just looking at the figure, you can get some sense of the heavy instrumentation of these airplanes. It was equipped with more control surfaces, more sensors, controls computers. And what they also did, they deliberately lowered the flutter speed of the airplane. These fuel tanks that you see near the tip of the wings, they installed heavy ballast masses at the nose and deliberately made the airplane flutter at very low speeds. And the goal was then to fly it beyond the flutter speed on active control and see how everything worked. This is, I don't know if you want to call it the beauty of the beast, phenomenal machine, very complicated, done in the early 70s. You can see in the nose area some of the added control surfaces. And Boeing demonstrated that indeed the airplane could fly on active control beyond the flutter speed, meet design requirements, just all using active control. So by the mid-1980s, where we were, aeroelastic optimization was quite advanced, not where it is today, but it was quite advanced. Of course, control system optimization was quite advanced too. So it was natural to ask, when we design an airplane, what if we integrated everything? What if instead of doing the structure separately and the control system separately, we would integrate everything into one optimization problem where everything will play together? And so before we go and talk about what was done in the 80s, I want to add a few notes. So far, I talked about the problem in a very analytical way. The control laws were some block diagrams, some mathematical expressions, and we talked about computers and structures. But it's not so simple. When you add a control system to an airplane, you add a substantial complexity to the system. There's no free lunch in the world. There's no free lunch in aeronautics. So we can control the airplane using a control system, but what is the price of the control system? These actuators, these computers, these data buses, all these hydraulic lines and the reservoirs, all this means weight and cost. And so again, without going into much detail, just to give you an impression, what you can see on the left is the architecture of the control system of the B-2 bomber. And this is a quad system. Basically, there are 4 systems, basically, that are designed so that when one or two of them would fail, the other ones will take over. So you will have quadruple capability in terms of actuators, computers, and things like that. That's heavy. That's complicated. That needs maintenance. So just talking about how you add controls and solve all the problems in the world is not going to lead you anywhere if you ignore this. On the right, you can see a typical F-16, and you can see, again, its actuators and its computers. The other very important question is the question of mathematical accuracy. The optimization process is a mathematical process. So every time we change the design, we have mathematical models that will tell us what happens. How do the stresses change? What is the flutter speed going to be? We have to have accurate mathematical models for the optimization process to make sense. Otherwise, we'll get nonsense. And we are talking about very complex systems. You have to capture by analysis the structural behavior, the structural dynamic behavior, the steady and unsteady aerodynamic behavior, and of course the behavior of the actuation system, the sensing system. This is not an easy job, even today. And so here is an example from the B-2. It's true this was done some years ago, but if you look at these diagrams on the left, you can see a frequency response. This is what happens when you use the elevons to affect the bending moment of the B-2, and you change the frequency. And you can see in the low range of the frequency, the broken line is the original analytical prediction, which was completely off. flight tests showed that they had a big error there, and they had to go back and fine-tune their mathematical models. If this were to be used for optimization, the optimization process would not lead you to the correct result. More recent results are from Dassault, from the same paper on the Falcon business jet. And again, just to get an impression, the analysis captures the behavior quite well. This is again some frequency response, some input, some output. But you can see that as you go higher in frequencies, there is a mismatch. What does it mean when you design a control system for something like this? So the accuracy of a mathematical model for real airplanes, and I'm talking real airplanes, not academic cases, simple cases, which are all nice and lead to many papers in the journals. I'm talking about what it would take to really affect the design process in industry. You must have accurate modeling in order to do meaningful optimization. So as it happens, things kind of congealed and popped up almost simultaneously in three places. One was Terry Weissar at Purdue with a student, Tom Zeiler, in collaboration with NASA Langley Aeroelasticity branch, Jerry Newsom there. And they wrote a very nice paper on the idea that it was time to integrate control and aeroelastic design. But their paper was really a concept paper, and they demonstrated it using a very, very basic, simple example. But when you talk about doing it with mathematical capabilities that would allow you to design real airplanes, it happens in two places almost simultaneously. At UCLA in the mid-1980s, and at the Polytechnic of Milan at about the same time. We didn't know about each other's work. I was working at UCLA with Lucian Schmidt and Peretz Friedman. I came from the Israeli Air Force. I had a lot of experience. I worked with the most advanced airplanes of the time, the F-16s and the relaxed static stability systems, the F-15s, the advanced F-4s. So I saw a lot of these aeroservoelastic problems in practice, and I had some ideas on what should be done. And in Milano, the great Paolo Mantegazza, with a phenomenal team of students, developed a similar capability, some differences. What we did at UCLA in the structures area, used some approximate models for wing structures that were good for fighter jets or supersonic jets, but not so good for high aspect ratio, subsonic passenger airplanes. Paolo Mantegazza and his team did it right. They used Nastran, they used finite elements. Great students, one of them, Sergio Ricci, who's here, talking about people that I'm indebted to. It's just so nice to have known him from his PhD days, where we found ourselves working on the same thing and now collaborating on other projects of active flutter suppression. So here is the problem formulation, and this was outlined in a paper that we wrote at UCLA in the 80s, and we published in the early 1990s. What are the behaviors that we are dealing with? So all these constraints, all these stresses, flutter speeds, levels of vibration, all these are what we will call behavior functions. You look at the system and you tell me how it behaves. So there are behavior functions which customers care about. So customer, you go in and you buy an airplane. What do you care about? What behaviors do you care about? You care about the cost. You care about the weight. You care about certain performance. It's a fighter jet. You want it to perform in a certain way. You care about safety. That's what you care about. And this is the highest level, basically, where customers talk to manufacturers about the airplanes that they want. But below, there are behavior functions. I call them secondary, but they are not less important. You have to design the airplane so that these behavior functions will be under control. First of all, in the structure area, every part of the structure has to have stresses in every maneuver, in every load that will be within limits. You may have some constraints on the level of twist and deformation. You may have some constraints on the frequencies. Customers, company, I don't know, Delta goes to Boeing to buy airplanes, they don't say, well, listen, in our list of specification, I also want to show me that this bolt in this part of the wing has a stress level that is below this level of stress. They really don't care about it, but the designer must care about it. In the aerodynamic area, we care about lift and drag. We care about any nonlinearity. We care about buffet. And so, again, we care about hinge moments because the moments on the control surface will determine the actuators. So again, I don't think that a customer will go to a company and say the airplanes that I want must have the hinge moment below a certain number, but the designer must, of course, tackle this. And in the controls, similar story. We care about the robustness of the system, how it can deal with uncertain situation. We care about the dynamic response that it gives us. And the aero-servo elasticity, now aero-servo is for controls. This is the traditional technical term, servo mechanisms for controls. We care about dynamic loads, so we care about flutter, we care about control effectiveness of the structure. So these are the behaviors. This will determine the constraints and the objective of the design. On the design variable side, we have design variables coming from the structures, the aerodynamics, and the controls. And there are 3 levels of them according to their complexity. At the lowest level is what we call sizing type design variables. So if we talk about structures, we talked about, let's see, yes, it works, great. I'm very happy that this PowerPoint presentation does work. So at the higher level, you have a structure, it has a shape, everything is connected in a particular way. You want to make sure that all the elements have the correct thicknesses, the correct area, so stresses are within limit. Now you go up in hierarchy, you're going to allow the shape to change. So you may say, well, here are the loads, but maybe the structure would be of a different shape that I started with. And on a higher level of complexity, you have topology, where you basically say, well, not only am I going to play with the shape and the sizing, I'm also going to play with how elements will connect points in the structure. Much, much more difficult. Same in aerodynamics. You can start with a given aerodynamic shape, but change with what you call the jig shape, how you would build it so that it will deform in flight to the correct configuration, and you can go higher and higher in hierarchy to play with the full shape of the airplane, and similarly for controls. So at UCLA, we created a code that could do all this for design variables of the sizing type. So it could play with composite layers of the wing and tailor them. It could play with control laws by playing with and adjusting the coefficients of transfer functions of the control laws. And it could play with the aerodynamics by designing the jig shape of the airplane. An example is a drone similar to the drones that I showed you, where in blue is the structure of the wings that we want to design. The skins of the wings are made of composites. There are 2 control loops. One is below, is the control loop that controls the elevator to make sure that the airplane does what it needs to do for maneuvering. At the tip of the wing, you can see a sensor, and you can see a control surface, and you can see a control law that will take care of flutter. And so here are some results. Everything is here normalized. What you see, the lines, the height of the lines, or the length of the lines is the mass of the wing, the weight of the wing. And we start with what is the unit. Basically, I normalize everything to the unit mass, what's called the stress design. Basically, here are the maneuvers. Find me the best structure that would meet all the stress constraints. Not flutter, not drag, just stress. Now, if we still play only with structural design variables, what we add some drag constraints. We say, well, that design that we got, we don't like the drag. We want to reduce the drag by 20%. Now, we have to play with the jig shape. And so now we find a mass of the structure. It's a bit higher, maybe 10% higher. But now you add a flutter constraint. The structure has to meet all the stress constraints, all the drag constraints, but also has to be flutter-free. Playing only with structural design variables, the weight jumps to more than 2 or 2.2 of the stress design. It's a huge, huge weight penalty. But if you add controls, if you bring the active control into the game, here we are. So the weight goes down almost to the weight of the structure without control, the weight of structure without the Flutter constraints. And here, when we add the drag design rules, we're basically bringing the weight to the stress design weight, paying no penalty for the control. Again, this is highly simplified. To be honest, I did not include here the effect of the weight of the actuators. I should have, but I didn't. And this is the work from Milano. At about the same time, they created a code named IDEA. And here is an example. The controller is very simple. They played later with more sophisticated controllers, but here you have it. And you can see again the iteration on a wing design where they use only structural design variables. The weight goes down to something like 145 kilograms, and then with the controls in the loop to 135. This is from Moti Karpel and Moshe Idan at the Technion, a very interesting parameterization of the control law, a kind of a mix of junctions where control signals meet and separate, simple gains where you just take a signal and multiply it, and also single input, single output, and multi-input, multi-output. That's the CISO and MIMO blocks, and everything can be then plugged into an optimization process in which you will optimize the structure and the control systems. They worked on a fighter jet in which they first optimized the structure, then they activated the control system and optimized the control system, and then they went back and fine-tuned the whole thing. And so the question that was brought up is whether we should do it this way: design the structure, freeze it, design the control system, and then back to the structure with the control systems, and back to a control system where we know how to design control systems to certain structures, and we know how to design structures instead of doing it in one shot. I was always a believer in the one-shot approach where you do everything at the same time, but I'm not sure I'm right. I'm not sure that the other way is not the same. Here is some work that we did at the University of Washington with my student Tim Jackson. We created this multidisciplinary aeroelastic, aeroservoelastic code, finite elements. What's special about this was that we used shape memory alloys. So we used strain actuation and articulated actuation. And we asked ourselves whether there was a best way, an optimal way, to use both, to use control surfaces that move part of the way in an articulated manner, and then fine-tune and create more complicated shapes using strain actuation, like piezoelectric or shape memory alloys. My great pleasure, I sometimes get emotional about it, is that Tim Jackson is now the head of dynamics and loads for Boeing St. Louis, in charge of all military programs at Boeing St. Louis, and soon I think at Boeing in general. Here's the control law in Tim Jackson's work. It's based, if you look at the equation at the top, these are the states in the dynamic model of the system. They describe aeroelastic states, actuation states, sensor states, gas load states, the traditional equations in state space of a dynamic system, and the control law tries to minimize this integral at the bottom, which, if you talk about it intuitively, is a kind of a superposition of two effects. On the left is some quadratic form of the displacements and the velocities, a kind of like a mix of strain energy and kinetic energy. And on the right is a quadratic form in the control effort, which tells you something about the control energy or the control powers that you need. And you play with these matrices, the Q and the R, in order to give certain weights to what you need. Do you want to focus minimizing the control effort, or do you want to focus on getting the response to decay as quickly as possible? We use those as design variables in this integrated design. Phenomenal work from Brett Stanford at NASA Langley. I'm showing the results of only one paper of his, but really talking about capabilities that he developed that is industry level, that is can do real airplanes. Finite elements, unsteady aerodynamics is used today in aeroelasticity, realistic models of actuators, accounting for the weight of the actuators. So he published a number of papers. We don't have enough time to look at all of them. This is just one selection. This is a passenger airplane with a CRM wing. This is the common research model. This is a model that NASA and Boeing developed for CFDers, basically, to compare notes. And one of the fathers of this, two of them actually, I think John Vosberg and Rick Waltz should be here in the audience. So don't look at the equations, look at the notes on the right. Basically, here are the constraints that Brett is accounting for. Maneuver stresses have to be within limits, no panel buckling. Hinge moments have to be within limits to limit what the actuators have to do. Some constraints on the work of the actuators, and then some constraints on manufacturing, on the thicknesses, and also on stiffness and aspect ratio, on stiffener aspect ratio for panels. And he also, for the controls, he also minimizes this quadratic measure from optimal control theory and LQR, linear quadratic regulator, the standard control theory measure of excellence, where on the right at the bottom is the control law, where the control commands are some matrix of gain times the states of the system. This kind of work, when you look at the left, allows us to look at trade-offs that before we just couldn't look at. So for instance, if you look at the top left, and again, I don't have a laser pointer here, so I have to kind of point you by talking, directing you. So you can see on the horizontal axis, you can see the control effort or the control energy. So the higher you are, the farther you are allowing the control system to work harder. For this is going to cost you. It will mean that you need more capable control actuators, and this will mean more weight, more power. On the vertical axis, you can see the resulting weight of the wing accounting for the actuation and the control surface. So you see, if you do not place a limit on the control system, that is, if you allow the control system to do as much work as it wants, you can bring the weight of the wing down significantly. But the moment you begin to limit the work of the control surface, as you move left, then the resulting weight of the wing goes higher and higher and higher, because now the control system is not allowed to help you as much as it would like. And similar results from the work at UCLA. So when you look at the figure on the right, these are three histories of an optimization where first, so what we're interested in is just the end results. So these circles that will appear, I'll go back, these circles that will appear will show you what is the end result. So this one shows you the result of optimizing a drone with an active control system, with flutter constraints, stress constraints, the whole host of constraints that I mentioned, but with placing no limit on the effort of the control system. Now, if you begin to limit the control system, the result is the system will meet the requirements, but the weight will be higher because the control system is not allowed now to do whatever it wants to do. And if you limit it even more, the weight of the system will be even higher. So it's consistency between the results that Brett got with these very sophisticated models, the results that I had, God knows, maybe, I don't want to think about how many years ago this was. Very interesting work from Stanford, from Ilan's crew. Very briefly, here they are designing a natural laminar flow wing. Here the idea is to get as much laminar flow over the wing in order to reduce drag by using optimization. So they use a maneuver load alleviation, and they use gust load alleviation to control the stresses in the structure. And then their design variables, in addition to structural design variables that decide how the wing will be built, also they have shape design variables that determine the plane form of the wing, how swept it's going to be, how slender it's going to be, also what the shape of the airfoil is going to be, and also some constraints on the pressure distributions to get you the laminar flows that you want. Beautiful work. Again, no time to talk about it in enough detail. But if you look at the figure on the top, and I don't know how well you will see this, but the green line tells you how much of the wing is laminar and how much of the wing is turbulent. And you see that on the left is an optimization of the wing. This is all published. This is all published in AIAA journals. So you can see on the left, just optimizing with natural laminar flow, but with no active control, you get the designs that you get. On the very right, you will see a design where you also focus on natural laminar flow, but now you have maneuver load alleviation and gas load alleviation. And so look what happens to the wing. First of all, a lot of it is now covered by laminar flow. Naturally, what makes it possible is that the aspect ratio of the wing becomes higher and the wing becomes narrower, the chords become smaller. And so a wing like this, without load alleviation and without gas load alleviation, would not do it. You will have to build a lot of weight into it structurally. But in the presence of active control, you can get this integrated multidisciplinary optimization and get an effective airplane. Now, I just sampled a few works in this area. Unfortunately, not much has been published. I was a bit surprised, actually, when I looked at the literature. I thought I knew. I was hoping that I missed, but not much has been published of this scope, this kind of work. I may be missing some very recent developments. But what I do want to mention very quickly is some really nice work from Kim Martens and his group, and Kim is here at the University of Michigan, where they used robust controls in order to optimize a UAV. Some work from Rafa Palacios at Imperial College on a very basic level, but really addressing some mathematical issues of optimization and the kind of design space that they had. And here is some recent work from Airbus, France, actually, which is promising. So, the issues. We're talking about huge problems, a lot of design variables, a lot of constraints, very, very demanding. This, of course, brings the issue of computing power, computing memory. We talk about the modeling of structures and aerodynamic in an accurate way and in a smooth way for optimization. What is the controller strategy that we're going to use? How are we going to parameterize control system designs that will work well in the integrated process? How do we design control systems that do a lot of things, that take care of flutter and ride comfort and all these other things simultaneously? Manufacturing has to be reasonably possible. What about going up in the hierarchy of design variables, from sizing type to shape type to topology? What about the math models of actuators? What about the locations of actuators on the structure? And then the predictive accuracy of the mathematical models, which are crucial if you want to do optimization. And then the design-oriented analysis that would work with the optimizer, the role of high-fidelity models and their surrogate approximations that we use for optimization, so that optimization is possible, and the big problem of uncertainty. So all this has to be done. If you want to make an impact on industry and how things are done, we must account for system reliability and redundancy. We must account for the actual cost of what we do in terms of weight and time, and actually what I missed here, also process time, in terms of how long it takes for industry to complete a design, and we have to remember maintenance costs. And so where are we? In terms of aeroelastic optimization, we are quite advanced. This is something, again, I stole from a paper from Kim Martens' group. So we know how to optimize structures in aerodynamics together with great fidelity. We know how to model actuators quite well, and if we don't, we can always test them on the bench. At the bottom, where it's not clear yet what to do, is how do you parameterize control systems and what kind of control strategy you would use. And this is just an example of different controllers. I'm not going to talk about it in great detail. It's enough for you to look at the picture and to see with the blue squares show you parameters in the control laws that the optimization process would work with. The jury is still out. It's not clear what is the best way of doing it. Here we are. So this is the problems we are facing. The design variables at their very different levels, the behavior functions, which represent the constraints and the objectives, and the mathematical model, which covers the airplane, all its systems, which have to meet all the constraints. So in this integrated aero-servo-elastic optimization, if we compare it to just aeroelastic optimization, and this is back to the Dassault figure, where are we? This is the Dassault figure. It shows you the development of aeroelastic optimization from the 70s until now. So in our area, where are we about here? Are we about here? I don't know. We are definitely not there. We are definitely not where we should be. Just at the same time, no need for despair. I truly believe that what I have outlined is possible and achievable, and it's just a matter of time. Remember, the structural optimization started with a truss structure, the 10-bar truss on the left, and ended with a high-speed civil transport configuration some years later. So I'm confident that what I'm outlining here is doable. What needs to be done is just more research, more tools development, more design process development because of the integrated nature of the problem, and very important, actually I had slides about it, except that the time limit here prevents me from using them, and I know you're happy. We're going to finish it on time. Education. Multidisciplinary education in aeronautics is more and more important. The systems get complicated. It's really important that we educate students who are at home with structures, aerodynamics, controls, airplane design, and aeroelasticity. At the University of Washington, we have a special master's track. This was actually developed because of a request by Boeing. Our first graduate was my master's student, Allison, is now working for Boeing Dynamics and Loads. And I think that every university should consider something like this to make sure that we have students, we send students into the world who are at home with the complexity of the systems that we are designing. And I'm done.
Thank you. Excellent. So, ladies and gentlemen, I'd like to thank Eli for a fabulous lecture, fully of the standard of the award and the recognition he's achieved. I don't want to upset the session chair starting at 2, so I won't be taking questions, but I would like to present Eli with a number of things, starting with his citation certificate for the award. And then we also have a rather nice, well, medallion doesn't do it justice.
Wow.
A large recognition piece. And then also our very own ICAS medallion, struck for the first time in 2022.
Wow.
And finally, you need a bag to carry this off the stage, a gift from Boeing, our sponsors. So please join me all in congratulating Eli on his award and appreciating the lecture just given.
Thank you.